Again, shellcode is a universal payload, so you can use this for control flow hijacking. Once you can hijack the control flow, for the next two labs, your main job is to change this instruction pointer pointing to the shellcode. Then shellcode will handle all these crazy situations so that you will get the shell. And once you have the shell, you can do anything on behalf of the process. In this case, our goal is to read the flag on behalf of this process. In this case, you can just invoke cat proc flag accordingly. But how to write the shell? We prepare detailed instructions. Not only that, we also prepare the shellcode.s. Whether you can use is a template of the assembly that you're gonna deal with. So let me quickly explain what is a shellcode.s and how this one actually work. Hopefully you get used to most of the instruction you're seeing right now from previous bomb lab. In fact, it doesn't contain much of difference. It only contains 10 or less than 10 different instructions used in this shellcode. So you should be able to understand one by one. But again, this kind of construction is not usual. The slightly different convention from first bomb labs. That's why we like to explain what's going on in this template. Again, it is well documented as well, so you can trace line by line. But let me explain a little bit more detail. And this is the header file that we included for invoking I think in this case we are using this particular macro here, the constant definition or system call number for exec CVE system call. So in order to use, oftentimes it changes, but most of the time it's actually free. But we don't like to keep remembering the actual value or constant for sys exec v. That's why I imported this header so that we can easily use the system call number for certain instruction set, certain system calls as well. And we also define some of the macro, which is actually very important macro you have to deal with for this tutorial. You first define some of the string, as you can see, is a bin shell. And if you type bin shell, you know what's going to happen. In fact, this is normal shell. Sometimes like Ubuntu, this is a typical convention to invoke the system shell, but most of the time their own preferences of shell that they're gonna support. In this case, Ubuntu actually using a shell called dash for this bare minimum shell. So in this case, we're gonna invoke the shell process or shell binary under the bin. And I think let me quickly show how it works first. So we also provide the make file as well. So if you see make file, it will also contain all the instruction to how to compile this particular shellcode and also how to extract the binary from them. But you can mostly use some of the building process and this particular test cases. So let me quickly show how it works. So what you have to do, you first replicate this tutorial file under your secret file. So mainly because you don't have a write permission, so you cannot simply build. So or you can download in your local computer as well. So I have everything here. In this case, you can type make. So we don't have target here, right? So if you type, the sequence of compilation commands is executed. In this case, shellcode is compiled with CC, and we extract the corresponding text section from the object file and create this payload. And then we prepare some of the target. And what's interesting here, we explicitly set this executable flag to the linker so that the target process actually contains executable stack. And then we delete this rm shellcode.object file. So if you type ls, you will see certain instructions like shellcode.bin. In fact, this is actually contain the list of instructions as a binary block. Okay. Apparently, you can now recognize most of them is indeed the binary. In fact, you can also disassemble pretty easily by using one tool that we can we're gonna introduce later. But in this case, you can type this particular command to figure it out. The actual instruction inside the shellcode.bin. So as you can see, this is the actual instruction we parse line by line. Apparently, this one is a little bit different from the shellcode that you're seeing in the left side, right? But in fact, it's actually exactly the same one. We simply strip down all these user-friendly command and immediate values into the actual binary instructions. And once we prepare this shellcode, the target binary is nothing but to accept the buffer from you. In this case, we provide the list of instructions. And for the debugging purpose, we provide this, hey, this is what we accepted so far. A simple for loop that printed out all this. And then this is a nice instruction that provide you the control flow hijacking. What it means is that we're going to interpret the buffer address as a function pointer, and we're going to invoke this function pointer in C. So in other words, if you provide any type of instructions here, and this buffer will be executed accordingly. So if you provide this particular list of instructions as a shellcode, apparently the target will execute this instruction one by one and ultimately provide the shell. So one way to do is just type test, then it will display this, and we provide and the program provide the entire shellcode.bin to the target process. So, but instead of just executing target as it is, of course you can do. You also nicely provide the debugging interface so that you can see we're gonna strace on the exec CVE. So whenever this target invoke exec CVE, we like to see such output. In this case, we can see by providing this shellcode.bin, the target at the end of execution, they invoke the bin shell with the list of this argument. In fact, this is a shell process that we are interacting with. So you can type ls. So if you type ls, you can see here the ls output is executed, right? And you can do many other stuff, like execute some instruction that is not exist, a command that doesn't exist, or in this case, you can, if you want, you can do cat per flag. In this case, again, we are under strace, so that you cannot get the actual flag accordingly. Our today's task is to understand this shellcode as it is, and then extend this one to invoke ultimately this command. So previously what we demonstrated is that we invoke the bin shell, and then we type proc flag. We type cat proc flag, so we get the flag. But what if process prohibit this exec system call or prohibit the invocation of the bin shell? So we are asking you to get the flag through exec system call that invoke the bin cat with the one extra argument. So previously we just execute this one program, but you have to invoke a process with this corresponding argument as an input. Okay, let me go through this one really quick. And this for macro is very important, but I'm gonna explain on the go. And in this line, we declare that we like to use Intel syntax, so which is nicely matched with your IDA or Ghidra if you're working with them. And we declare this a text section so that the rest of the section will contain instructions accordingly. And then we define a function and expose this main so that we can deal with, we can start locating this main starting from here as well as a symbol. And very first instruction is pretty interesting. We just jump into the call address. And where is the call address? It's actually in the bottom. So when call instruction is jump, you can imagine the instruction pointer is starting from here. Change it to the very first instruction that this label is pointing to, in this case here. Interestingly, the very first instruction in this case is call. What it means is that we're gonna, similar to the function call, we're gonna call this pop laddr. In this case, we're gonna call these particular locations as if this is the function. But behind the scene, whenever whenever we execute these call instructions, behind the scene, we're gonna push the next instruction pointer, in this case, the line 38, onto the top of the stack. We're gonna change the instruction pointer to pop laddr. In this case, now our instruction pointing is pointing to here. And meanwhile, on top of the stack, as a return address, now contain this particular string. So when we say .string, then you simply say we simply indicate that this byte, in this case the bean shell, is actually injected here as a string. So what does mean is that on top of the stack, as part of the return address, although it's very unusual because it's now pointing to the data, not instruction pointer, right? But our instruction pointer happen to point to the certain data that we are interested in this case, a bean shell. And once you pop the value on top of the stack, in this case, the pointer to the string, the bean shell will be stored as part of the ESI. And what we are going to do is pretty interesting. We actually prepare some of the argument to exec CVE, but the exec CVE instruction or system call in C accept what we call list of the C array. If you're wondering how exec system call work, you can type man exec CVE, and it actually contain as a first argument you have to provide the file name, but as a second argument you have to provide argv vector, which contain the very first argument, in this case file name as it is basically what you call as a program name, and you're going to provide this environment variable pointer. So when we say C array, in this case, it's an interesting way to represent a vector in C. For example, so we actually saw this format. So this is an interesting way to see what's going on. The very first argument to the exec v is just C string. Second one is actually array that containing a pointer to the target. In this case, we didn't provide any argument by us, but in fact, as argument 0, the system provides the target as a first argument. In this case, if you want to change the process name, this is the place that you change those names. And in order to indicate the end of array, as a convention in C, we're going to provide the target and null pointer as a part of it. This is a simple way to represent the vector in C array, through the C array. So once you understand this convention, this is exactly what we are doing. We are constructing those conventions in the memory, in this case starting from this string. But let me explain this one a little bit more. And ESI contains the beginning of the bean shell string, and we're going to prepare the argv. In this case, we're going to prepare this array. And as a first argument of the argv, we're going to put a pointer to the target, right? We now have C array that contains the target as a first argument. Then what is the argv? The argv is nothing but a constant starting from these locations. Because ESI pointing to the location here, when you move up to 7 and plus 1, and this basically contains the 7 character, and plus 1, which means you skip the last null byte, and you're going to use the rest of the space as argv locations. So we are preparing the argv vectors right after this string. So what just happened here is that if I visualize a little bit, so this is the location that we're going to deal with. This is the location that we're going to deal with, and our ESI is pointing to the very beginning of the string, and this one contains bean shell, and there will be null character that we're going to inject later, null byte, and then argv in this case pointing here. But the reason that we use this capitalized argv as a constant is that this particular location is dynamically determined and now contain ESI. The argv constant now pointing, indicating the size from the beginning of the bean shell all the way to here. So argv is a constant that if you add from ESI, then it's now pointing to the argv array here. So what we just did is that in this particular instruction, we're gonna put the ESI in this location, which means we now have a first argument ready that pointing to the bean shell. What should be the next argument of argv? Next element in the argv array, it should be null, so that we can indicate that we only have a pointer to the bean shell as the first argument of the argv, so that we can actually construct this type of array vector in C. There are a few nice tricks that we're going to discuss. Is that once you set up this first argument through ESI, which means we prepare the first argument element of the argv, and we initialize with the 0 value by XOR this EAX. So whenever you do XOR EAX and EAX will contain 0 value because it's exactly the same value you XOR. Why we are doing this? In fact, there are many reasons we actually do. You can do move EAX 0 value. Of course, that's an easy way to do, but unfortunately, your shellcode ended up having an interesting character in it. In this case, it's a null pointer. So when you send this shellcode to the remote setting, remote program, or inject it to some process, likely you're going to send this as a string, which we really want to avoid this type of character in your shellcode. So instead of using move EAX0, we're going to do this trick so that we can have, we can set the EAX to 0 value, but still without containing null byte in your shellcode. And then we're going to put a 1 byte. In this case, we can access a 0 value into 1 byte 0 value through AL register, lower byte of EAX register. And then we're going to put it to the string length. In this case, again, the string length is pointing to the end of this string in this particular location here, so that we can make sure the string is actually ended with the bean shell. And then once you do, we're going to set up another 0 value, in this case null pointer, to the environment vector plus ESI. And this is a pretty interesting one. For example, in exact CVE, not only you provide a list of the argument as just first argument, you can also provide a list of environment variable as a second vector. So as you can see in the convention of CVE, so I like to get the C vector with the environment, right? In this case, that in our shellcode, we actually ignore all these environment variables and provide the empty vector. And this location is pretty interesting. Right after this string, the argv vector locate, and as a first argument, it contains the pointer to the bean shell. As a second argument, we like to put as a null. And one interesting trick that we are using in this shellcode is that the end of argv and environment variable actually share, so that we don't have to we don't have to create extra byte to handle this environment variable separately, because it's the same null vector to us as well. So once you set this environment vector, all the argument is just ready. We now have a first argument. In this case, we also have argument for environment variables as well, so that it's a matter of just injecting them, right? So once we have this, we like to invoke the system call through this particular instruction, in this case, interrupt 80. So this is a simple convention that you invoke the system call. In fact, there are many conventions of system calls as well, and it also depends on the particular architecture. But we are dealing with 32-bit x86 platform. In this case, this is what we call 32-bit x86. In this case, i386 is actually represent how to invoke a system call, or basically how to communicate with the kernel, so that we're only looking at the interrupt in 80, and system call number should be injected in EAX, and return value will be contained in EAX, and etc. in the second return value as well. Also, there are a lot of interesting conventions that you should check as well. And this is a list of the argument that we're expecting when you're invoking system call. So as a first argument, we set pointer to the set the value to EBX. In this case, we set the beginning of the bean shell to EBX, and then we're gonna calculate a little bit so that we can point to the argv vectors and environment vectors as a first, a second, and third argument. So in this case, when you invoke this int 80, the system call execv is invoked because we indicate through the EAX that hey, this is a system call that we like to invoke, and then the kernel will look up the system call table and fetch the corresponding routine, the dispatcher, and provide this one as an argument. The one as a string path name, the second is argument vectors and environment vectors accordingly. So once we execute this, and system will execute the bean shell, invoke the bean shell as a child process. So our task again, and the rest of the system code is pretty similar. We like to terminate the process if just in case the execv doesn't work very nicely. And in fact, the way we deal with is pretty similar to the previous routine, but instead of getting the actual system calls through this, of course you can get it, but unfortunately, the way we can inject those as ended up having null bytes in the system call. That's how we deal with this. That's how we deal with this in this case. So we like to do exit 0 so that instead of clearing up the EBX register and move to EAX, increment the EAX, because the exit system call is actually 1, and then we invoke the system call so that we can invoke the exit system call with 0 as a first argument. Basically, return value to the parent. So given this setting, how can we modify this one to bean cat? In fact, without having clear understanding of the shellcode assembly, in fact, it's very challenging. So before we jump into this particular modification of this shellcode, we highly recommend you to understand this every single instruction here and start working on. So as a first thing first, can we modify this one? This is not the So this is the file that we can modify. Let me quickly explain what we can do. So let's see how many people here. So feel free to leave. We're gonna record that anyway. What main file is that? What do you mean? You can just type man syscall. The syscall is typically in the system as a man file, so you can check their contents. Okay, if you guys are interested in, I can keep using this time, probably maybe 10 or 20 minutes more. So okay, sounds good. So first thing first, we're gonna modify to bin cat. Pretty easy. We can do instead of bin cat. It's nicely macro, so that instead of saying 7 character, if you say 7 character, this C will be overwritten. Right? Do you get that? Let's try. So, well, we like to invoke bin cat, but unfortunately, the C is discarded because our string length didn't point to the right null character correctly. What should we do? Modify to 8. C. So if you start executing this, you can see the bin cat is invoked. Again, our first argument is nicely bin cat as well. If you type ls, unlike previously that displayed the file, this cat is actually working, echoing with whatever data that you're putting, right? Good, that's easy. Then how can you put the second argument? The second argument of this particular invocation, right? That's the main question. So currently, we are using argv, which is right after this guy, right? Say this is 8 bytes. There's 1 byte that we're gonna use, and this 4 bytes is the beginning of the argv, right? So this pointing to here in bin cat, whatever cat here. And then our goal is to modify this guy, right? And containing to some string, in this case, pro flag. And similar to what we did here, this should be null. Not only that, the environment vector p is pointing to here. And this is our ultimate location, that ultimate construction that we are doing. So where to put this string? In fact, there are many places you can put right after these guys and etc. But the trick that we're gonna do is that, in fact, we have a capability to inject a null bytes. So right after this, say put any null byte, say the locate. It doesn't matter. You can put any bytes here, any character here, and proc flag. How many string? 19. Say this is a 19. But I also want to indicate there. So let's try this. You know, we say apparently say bin cat this guy. If we inject a null bytes nicely here, right? Then what's going to happen? In fact, consider it's a bin cat. So let's do this one first. But before we do, we have multiple string here, string 1 and 2. In this case, bin cat and proc flag. So it's better to keep track of what we mean by this. Say there are 2 strings in this case, bin cat and proc flag that we like to deal with. Say there's a 2 string. What should be this guy? So right after my full string, so we like to put string 2. And any other place that we use? So this is should be 2, because we are modifying the first argument accordingly. And so let's do this first. Let's try modify the end of bin cat and see if we can invoke bin cat without having this proc flag, unlike this guy. So as you can see, although we provide bin cat with another character and proc flag, the 1 byte between them is actually truncated very nicely with the null character. so that the program considers this is the end of the C string, right? That's nice. Then how can you utilize the proc flag? So our goal again is to manipulate. So this setting is a little bit changing right now. So instead of this guy, and here, oops. Oh, okay. Instead of having this one string, in fact here, we put the proc flag, right here, and we like to also put extra null after the proc flag so that we can maintain this one is nice one string, and instead of having just one pointer here, we like to point to the next one. In fact, these locations are pretty easy to infer from the beginning of the ESI, but unfortunately ESI is everywhere, so pick another one. Say EDI, seems like natural choice. We replicate ESI to EDI. EDI is not used anywhere, and using EDI to create or contain the pointer to the proc flag. In this case, EDI containing now beginning of the string. Then how can we modify this? In this case, we can say the beginning of the string 1 plus 1. So if you proceed to, if you add string length 8, then that we are pointing to here. If you plus one more, now pointing to the proc flag. And we now have EDI, the proc flag here. We're gonna put it to the second argument of argv. And once you set this, let's move it this way, right after. And this is the first argument. How can I put the next argument? We like to put EDI as a next argument. In this case, next argument is a 4 pointer, so we're gonna move with the plus 4, right? In this case, now we have in this figure, we're now putting a proc flag pointer here to the second argument of the argv. But there's one caveat. We start overriding involvement variable. So involvement variable, the vector to the involvement variable pointing to the end of the argument vector, because we now have two element inside the arg vector, we now should point to the next element. So that in this figure, the involvement vector, instead of pointing to here, arg plus 4, by pointing to here by plussing 8, by skipping the second argument. And again, similar to the previous one, the last element, the null bytes, null pointer, will be shared between them. Let's see. Sounds good. I think one potential caveat is that, as you can see here, I think make sure that the second string is actually ended with the null as well. But I believe the second string is actually containing the null. But if you're very cautious, you can actually overwrite the second string here with the null as well. But because everything is, I'll say, fgetted through the C string, in fact, we don't need this particular line. But for the cautious revision, okay, it seems to just work. Let's see. In this case, we have bin cat as a first argument, and we have as a second argument, we have list of vectors that contain a string to the program name, and the first argument that we like to control. In this case, the proc flag, right? Mean, by using EDI, we nicely calculate the location of the proc flag, nicely put the null character as the last element of this first argument. The second argument is the argument vector. We also provide the null pointer, the empty vector, to the environment variable. By doing so, you can see this is a 0 variable inside. By doing so, we can nicely control the exact feed. By invoking this, bin_cat is invoked with the proc flag as argument, so you can actually get the flag. But again, this is for debugging purpose, so that if you want, you can delete the target, which will be generated with our privileges for nothing. You can tutorial target. So create a symbolic link here, which means now if you invoke the target, we indeed invoke the target process as you wish. And instead of invoking the local target, you can actually invoke the original target that you need to get the flag. And this is a way to get the flag. And this process is executed and execute with this particular privileges, in this case Tut02 shellcode. And with this UID, the process is executed and provide a flag because we change the control flow of the target, and they executed the instruction by instruction from the shellcode payload that we provided as well. I think that's all for today. And if you guys have any questions, I am happy to answer anything.